Hello everyone and welcome. My name is Mohammed Safa. And in this video, I will present the paper entitled Comprehensive Analysis of Near-Ultrasonic Acoustic Channel for Short-Range High Data Rate Aerial Acoustic Communication. So let's get started. First, the paper is structured as follows: introduction, channel characterization, implementation, experimental results and discussion, and finally, the conclusion. Introduction. First, let us see what we mean by AAC or Aerial Acoustic Communication. All the available mobile phones around us contain speakers and microphones. These can be used typically for recording or listening to audio signals. However, they can also be used for communication applications, meaning that the transmitter can use the speaker to transmit information on the audio signal, and the receiver can use the mic to record the signal and to demodulate the information. So simply, AAC is the use of the speakers and microphones that are available in the various devices around us for communication applications. The main challenges facing AAC systems are first, frequency selectivity, meaning that the frequency response of the channel is not constant over the communication bandwidth, or signal attenuation. And the main research direction can summarize as follows: either increasing the communication range or increasing the data rate, which is the main focus of this paper. The aim of the paper is simply to analyze the effect of the near-ultrasonic acoustic channel to enable high data rate aerial acoustic communication implementations. The effect of the channel is either multipath fading effect or Doppler shift, which mean the frequency shifts that happen if there is a relative movement between the transmitter and the receiver. And the multipath fading effect is calculated or measured using the multipath fading parameters, which they are the mean excess delay, the root mean square delay, and the maximum delay. And the multipath effect is calculated using a reference signal, which is transmitted on the transmitter and then recorded on the receiver. This signal then cross-correlate with the reference signal or with copy of the reference signal. And from the peak of the correlation and the delay, the multipath parameters is or are measured. So here we can see the autocorrelation of the signal. The signal has a distinguished peak, and then it has a relatively small other peak. So from this peak, we can measure the delay and the value of the paths. And for the Doppler shift, we also use a reference signal, a periodic reference signal with period T. This signal is also transmitted on the transmitter and then recorded on the receiver. And then the phase shift between one period is measured. And from this phase shift, the Doppler shift or the frequency shift is calculated, which is here, we call it FD. On implementation, we have the implementation block diagram as can be seen here. First, we have reference signal. We have two reference signals, one for calculating the multipath fading effects and one for calculating the Doppler shift. This reference signal is then up-converted to the near-ultrasonic frequency band, which is from 18 to 21 kilohertz. Then a bandpass filter was used, and then the signal is transmitted using the speaker. On the receiver, the signal is recorded using the mic, and then a bandpass filter is used to filter any unwanted noise. Then the signal is down converted to baseband, and also a low-pass filter was used. And finally, the Doppler shift or the frequency shift and the multipath parameters was calculated. Experimental results and discussion. First, the multipath fading. We calculated the multipath fading for two cases, the line of sight case, as can be seen here, and the non-line of sight case, as can be seen here below, at various distances d. So first, for the line of sight case, here we can see the correlation of the transmitted signal that was received on the receiver and then correlated with the reference signal. Here at various distances, 0.25, 0.5, 1, and 2 meters. And for the line of sight case, we can see that we have only the main path. We cannot see any multipath effects. And here, in this case, the frequency selectivity is solely due to the hardware, due to the speaker and the microphone, and not due to the multipath fading effects. However, in the non-line of sight case, here we can see the multipath effect clearly. So for example, at shorter distances, here we can see we have a multiple version of the transmitted signal at various delays. If we increase the distance, here we have a larger delay. And for larger distance, we can see also a more delay with more version of the signal that received. And if we increase the distance further, we can see we have a lot of versions of the transmitted signal at various delays. So here each point means that this, for example, this is the main path. This is other version of the signal, other attenuated and delayed version of the signal. This is also other attenuated and delayed version of the signal. And from this correlation, the multipath fading parameters was calculated. And they are summarized in this table. We can, as expected, we can see that as the distance increases, the multipath fading is also parameters, or the multipath fading effect is also increased. As we can see, we can have up to 32.7 milliseconds of maximum delay at 2 meters. For the Doppler shift or the frequency shift was also calculated using two cases. The vertical movement, meaning that the transmitter is moving toward the receiver and moving back. And the other case is the horizontal movement, meaning that the transmitter is moving to the left and to the right relative to the receiver. And the Doppler shift or the frequency shift was calculated for the two cases. Here we have the vertical case. We can see we have a frequency shift of up to approximately 40 Hertz with average of less than 30 Hertz. And for the horizontal case, we can see that we have a frequency shift of approximately 20 Hertz with average of less than 20 Hertz. And we can see here we can have a variation of up to 20 Hertz per second on average. So in conclusion, this paper analyzed the effect of the multipath and the Doppler shift in the near-ultrasonic acoustic channel. And we saw that in the line of sight case, we have only line of sights. We have only one dominant path, and the frequency selectivity is solely due to the hardware. However, in the non-line of sight case, we saw that we have a significant multipath fading effects with a maximum delay of up to 32.7 milliseconds at 2 meters. For the mobility, we saw that we can have a Doppler shift or a frequency shift of up to 40 Hertz and a maximum variation of 20 Hertz per second. For future work, we are using the reported results here to implement a high data rate aerial acoustic communication system in the near ultrasonic frequency band. And thank you for your attention.